Okay, so this section is focused on metabolism, and this is going to be an important topic throughout our time, both in AMP1 and AMP2. There's an important focus on how cells get energy, where that energy comes from, and how we metabolize it. First good question is, what is metabolism? Um, a lot of people think that they understand this term, but then it turns out that they really only half understand it. When we think about metabolism in standard everyday culture, what you're really thinking of is catabolism, which is what we're going to be talking about in this video, but metabolism actually has two parts. Metabolism is the total of all chemical reactions that happen in the body. It's so important. I'm going to understand all here. All chemical reactions that happen in the body, regardless of whether these reactions are building things up or breaking things down. The metabolism is broadly divided into two categories. One is catabolism, the other is anabolism. Here we see those two suffixes that we talked about early on when we were talking about atoms and ions. We said that there were two types of ions, cations and anions. Those are not at all related to catabolism and anabolism necessarily. But these are prefixes that are often used in science to specify two things that are like opposite of each other or opposed to each other. Catabolism is what we usually think of as being metabolism, right? If you say like, oh, I've got a fast metabolism or I've got a slow metabolism or something like that, what you're talking about is the rate at which your body breaks down nutrients like sugars and fats and stuff like that and liberates the energy from them. That's what catabolism is. Catabolism is breaking down big things into small things. When you break down big things into small things, you usually release energy and building blocks. There are two things that you need to make new biopolymers: energy and building blocks. You got to have something to build them out of, and you got to have the energy to build it. That means that if you're going to make things, you need building blocks and you need energy. Catabolism is how you get that. That's going to be the focus of this video. The next video is going to focus on anabolism. Anabolism is all of the reactions that are focused on building things. Taking energy and smaller building blocks, putting them together, mostly through the process of polymerization, to build large, complicated molecules. So catabolism is your body's energy economy, the way your body gets energy. And you don't get energy from just one source. You actually get energy from several sources because it's really important. You don't know what you're going to have to eat tomorrow, so you've got to be able to metabolize whatever it is that you're going to eat. Mainly humans and other animals get their energy from carbohydrates, proteins, and fats. These three elements, carbohydrates, proteins, and fats, the pathway starts differently for all three of them, but all three of these, in the vast majority of animals, will end up feeding into the same pathway. So we've got carbohydrates, we've got proteins, we've got fats. And all of these have different initial breakdown pathways, but they all basically feed into a pathway called the citric acid cycle. You may also hear this referred to as the tricarboxylic acid cycle, the TCA, or the Krebs cycle. I'm going to refer to it by the citric acid cycle in here and in class, but you should be aware that you may see the other terms in textbooks or in future classes. From the citric acid cycle, we're going to take the energy, and specifically the electron energy, from all of these things, and we're going to use that to make ATP. I'm going to start off talking about carbohydrates. Then I'll talk about proteins and lipids. And I'm going to take them all to the point where they all feed in commonly to the citric acid cycle. Then I'm going to talk about the citric acid cycle, and then the electron transport chain and ATP synthesis, and take you through basically like what's different about how your body metabolizes carbohydrates, proteins, and fats, then take it through the common pathway all the way to this is how you make your ATP. Carbohydrate catabolism, breaking down sugars, has basically 3 steps to it. The first step is called glycolysis. And if you'll recall, gly means sugar, and lysis means to cut. Literally, this means cutting the sugar. This process happens in the cytoplasm, by the way. Most of these early steps in lipids, proteins, carbohydrates, those happen in the cytoplasm. The citric acid cycle and everything after that happens in the mitochondria. All right, so glycolysis. You start off with your sugar molecule, which I've drawn here as this hexagon, and this sugar molecule is full of energy. That's why I've drawn it in bright yellow. During glycolysis, the cell is going to extract energy from this molecule. And specifically, most of the energy that we're extracting is in the form of electrical energy. Remember that these are carbons held together by bonds. And those covalent bonds are each a pair of shared electrons. What we're going to be doing is breaking these bonds. Remember, it's the cutting of the sugar. We break these bonds, and when we do, we take the high-energy electrons that made them up, and we're going to store them. And you can't just store electrons just sitting there. You can't put electrons on the shelf. They have to be connected to an atom. So in this case, the atom that we're going to use is NAD plus or NADH, right? NAD plus is the energy poor form. This can hold electrons. This NADH is the energy rich form. It is what it becomes when you put electrons on. So NADH is energy and electron rich. That's why I've drawn it here in yellow. All right, so we're going to take the electrons off of glucose, store them on NADH. This NADH is going to be used later on, but we're not using it right now. This process is very favorable, And we can actually capture some of the extra energy. We're storing most of the energy on NADH, but there's some extra energy that we can capture and make ATP. Specifically, we're making 2 ATP at this step. And we just took the energy out of this glucose, so it's now going to be removed, right? So we've got less energy in here. I took away some of the yellow sheen to it. And we've broken the glucose in half. We've cut the bonds, and we actually end up with 2 3-carbon sugars. This is a 3-carbon sugar. This is a 3-carbon sugar. These 3-carbon sugars are called pyruvates. That's the name of the chemical. What goes into glycolysis is glucose. What comes out of glycolysis is 2 pyruvates, an NADH, and 2 ATPs. Actually, it's 2 NADHs and 2 ATPs, because you had to break 2 bonds. So the next route for our carbohydrate metabolism is what's called the transition step. This actually occurs as the pyruvate is moving into the mitochondria. So glycolysis happened in the cytoplasm, but everything else is going to happen in the mitochondria. We got to get this thing into the mitochondria. And as it moves in, we're going to actually suck a little bit of energy out of it and change it. Right? So during the transition step, we're going to take pyruvate and bind it to a cofactor called coenzyme A, or CoA. When CoA binds to pyruvate, it will cause one of the carbons to leave as carbon dioxide. So you can see here, this carbon is leaving as carbon dioxide, and we now have 2 carbons bound to CoA. The name for a 2-carbon is acetyl. So if you think like an acetylene torch, that's actually burning 2 carbon compounds. And so this is called acetyl-CoA. It's an acetyl group bound to a CoA. And we released this CO2. We broke a bond when we did that, and there's some electrons we can capture from breaking that bond, and so we store them as NADH. Acetyl-CoA is the common starting place of the citric acid cycle, and it's now moved into the mitochondria, and we'll see that most of these metabolites eventually go to making acetyl-CoA, and then acetyl-CoA goes into the citric acid cycle. Right, so next is proteins, and we're going to take proteins to where they go. All proteins basically start with this structure. You have first you take your protein, you break it down into amino acids. Your amino acids have an amino group, and they have a carboxylic acid group. They've got this carbon here, and then they have their R group. There are 20 different R groups. So there's 20 different amino acids, and they're all going to yield slightly different products, but there are a few things that are common to them. First is this amino group. It's got to go. And it goes through something called oxidative deamination. Oxidative means breaking bonds. Deamination means removing the amine. And we broke a bond, so we're going to capture some electricity in NADH. The reason why it had to go is The citric acid cycle doesn't do anything with ammonia. It can't handle it very much. So we have to remove the ammonia before this is going to get to the citric acid cycle. And there's a little bit of an issue because ammonia is toxic. And as you saw, the NADH went to the mitochondria. That's where it's going to be used. And the ammonia is actually shipped to the liver, right? And the liver converts the ammonia into urea. Urea is less toxic than ammonia. It's not non-toxic, but it's certainly less toxic than ammonia. And so you store that in, well, the little bit of it goes into your blood, and then from your blood it gets filtered out by your kidneys. In your kidneys, that urea forms a large portion of the urine that you excrete. So urine is your process of getting rid of this toxic ammonia, well, among other things. But getting rid of this toxic ammonia that comes from amino acid metabolism. This thing here that's left can be metabolized a couple of different ways depending upon what the R group is. It can be converted to pyruvate. And if it's converted to pyruvate, then it goes through the transition step and then into the citric acid cycle. It can be converted directly into acetyl-CoA, and then the acetyl-CoA just goes into the citric acid cycle because that's where the citric acid cycle starts. Or it can be converted to other citric acid cycle intermediates, and then it actually won't join the citric acid cycle at the beginning, will instead come in part of the way through. This just depends on which amino acid it is that you are metabolizing. It can also be converted into glucose or lipids, right? So I used to have when I was a kid, my health instructor, who it turns out didn't really know what he was talking about, told us that you can only get fat by eating fat. That if you just don't eat fat, then your body won't have any fat. This is wrong. Your body is actually perfectly capable of converting one sort of nutrient into another. So for instance, even if you're on a high protein diet, you're eating just protein, like maybe you're just having protein shakes, your body can take that excessive protein. If you're drinking more protein shakes than you're using, your body takes that extra protein, breaks it down into amino acids, deaminates those amino acids, and then it can convert those amino acids into glucose, which can then be stored in your liver in the form of glycogen, or convert it into lipids, which are then stored in your body in the form of fat. You can convert glucose into lipids. You can convert protein into lipids. You can convert glucose into lipids into glucose if necessary. It's hard to convert things to protein because you have to add the ammonia to it to get protein back, and you just peed out the ammonia. So you get most of your ammonia in the form of eating proteins. So if you don't eat any proteins, you will eventually become malnourished and incapable of making new proteins, even if you're getting plenty of calories. But all the other things are freely convertible. Last, we have lipid metabolism. And lipid metabolism, to a certain extent, is the easiest, at least chemically speaking. And you'll see here why lipids have so much energy. Remember that each amino acid is going to make like one pyruvate or one acetyl-CoA. Each glucose is going to make 2 pyruvates and thus 2 acetyl-CoAs. Well, one lipid molecule is actually much longer than this. Most lipid molecules have between 8 and 18 carbons on them. So this would be like one of the shorter lipid molecules that you might find. How are you going to metabolize this? Well, the first thing that you do is you eat triglycerides, which are 3 fatty acids bound together by this sugar molecule called a glycerol. In your stomach, you digest that. So you remove the fatty acids from the glycerol. Glycerol actually gets metabolized in the citric acid cycle because it's one of the intermediates, or it's related to one of the intermediates. And the fat itself can either be stored or broken down. When that fat is broken down, what happens is you move CoA in and you attach it to the end. And then you break off 2 carbons through a process called beta oxidation. It's called beta oxidation because carbons are named starting from the end. So this is the alpha carbon, this is the beta carbon, this is the gamma carbon, and past that point it doesn't really matter. It's called beta oxidation because it's this beta bond, the bond after the beta carbon, that will be broken. Remember, oxidation usually means breaking bonds. We'll get into sometimes when it doesn't later on. So we break that bond. What do we have? We have an acetyl-CoA. This is acetyl-CoA. And it can just go right to the mitochondria for further metabolizing. Then we can bring in another CoA, break off another acetyl-CoA, and then do it again and again. This acetyl-CoA goes directly into the citric acid cycle if it's feeding the cell that the lipid is coming from. But your lipids, your fats, are actually mostly stored in specialized fat cells called adipocytes. These adipocytes are mostly for storage. They don't actually need a lot of energy. So what happens when you don't have enough sugar? You're on a low-carb diet, say. What is it that needs the energy? Well, your immune system needs energy, your muscles need energy, your brain needs energy. All right? Where's that energy going to come from? You don't have any sugar in your blood, so because you're on this low-carb diet, many of you have probably heard of ketonic diets or going ketonic. Where do those ketones come from? Well, acetyl-CoA itself is actually not something that your body's very good at exporting to other cells through the blood. With sugar, you just put sugar directly into the blood, and then other cells respond to insulin, and they take that sugar up. No problem. If you did that with acetyl-CoA, you would run out of the CoA, right? So usually in the citric acid cycle, this CoA is released, and then you keep it around to bind something else. But if you were binding it to things in your lipid cells, your adipocytes, and then shipping that off to the brain or to the muscles or whatever, the CoA would drain from your adipocytes to your muscle cells. You'd have to ship it back, and that's hard. So instead, you take this acetyl-CoA and you convert it to something called a ketone. And these ketones are soluble, and they can be put into the blood. So you put the ketones into the blood, and then, just like with sugar, other cells can grab those ketones, and then they can take the ketone and attach a CoA to it, and in doing so, they will regenerate the acetyl-CoA. Just a second here, my control mechanism broke down. There we are. This is that process called ketogenesis Literally, genesis means creation. So this is the creation of ketones. You start off with 2 acetyl-CoAs. That's acetyl-CoA. This is a carbon right here. This is a carbon right there. You have an enzyme called thiolase, which is going to remove one of the CoAs. CoAs, by the way, have sulfur groups in them. And when you do that, you're going to attach these 2 acetyl groups together, making a 4-carbon compound. You have another enzyme that's going to remove, basically add another CoA onto it. So now we have 6 carbons. And then we remove an acetyl-CoA, this one at the end here, making a 4-carbon. And that's basically because we need to keep it soluble. This that's made here is what's called acetoacetate. And acetoacetate can be converted into 2 forms. It can undergo non-enzymatic decarboxylation, where it loses CO2 naturally and then becomes acetone, which is a ketone that your body uses. Or you can put some electrons on it using NADH, and that will convert it into D-beta hydroxybutyrate. This is actually the most useful form of ketone. But you'll find both of these things in your blood if you're on a ketone metabolism. And most of the cells of your body can use either of these things and just run this process backwards. That's why all of these things have arrows pointing in both directions. Run this whole thing backwards to make 2 acetyl-CoAs. Your liver can then take those acetyl-CoAs and turn them into glucose, which it stores as glycogen. Most of your other cells in your body can then take the acetyl-CoAs and use them in the citric acid cycle to make energy. The exception to that is your brain. Your brain actually can't use ketones for energy. So if you're on a completely ketogenic diet, you will actually eventually start to suffer from brain starvation. But your liver can make glucose from ketones. So over a long period of time, it can get usually enough sugar in the blood to support moderate brain activity. But one of the things that happens with people who are on a heavily ketonic diet is the brain is being malnourished and will start to go a little fuzzy after a while. All right, so we've talked about how all of these things get to acetyl-CoA, and we said that acetyl-CoA feeds into the citric acid cycle. I'm not going to go over all of the reactions here. I'm just going to give you the highlights of the citric acid cycle. Right? Acetyl-CoA is the starting point. This is called a cycle because it goes around in a circle. The first thing is that acetyl-CoA is going to join with this chemical called oxaloacetate. And the last step we're going to do is actually convert back into oxaloacetate. So that's why it's a cycle. We're going through, we're going to use up the acetyl-CoA, but we will regenerate the oxaloacetate, which will then go around for another round. All right? Oxaloacetate and acetyl-CoA join together. CoA leaves. Now, some important things. You can see that there are a whole bunch of different steps here, but there are a few of them that matter a lot. All right? These are going to be the steps where you break a bond and harvest some energy. So here, well, these two, really, to start off with, are both steps. Remember, our acetyl-CoA has 2 carbons. In both of these steps, carbon dioxide will leave. So the carbon goes away, and you'll eventually breathe it out. When you break the bond that held that carbon in place, you capture the electrons in NADH. So for every time that this citric acid cycle goes around, we're going to make 1, 2 NADHs. Next, this step here is fairly favorable, and we're going to harvest the energy from that to make 1 ATP. Third, with this step here, we actually we don't have a carbon dioxide that's leaving. We're not breaking a primary bond, but what we're doing is actually note that this has no double bonds. This does have a double bond. We're forcing the molecule to share more electrons. When you force it to share more, it liberates some, because now that it's sharing more, you've liberated some electrons. We're going to store those electrons on a molecule called FADH2. FADH2 is like NADH's little brother, right? It holds electron energy, but they're less energetic electrons than the NADH are. After that, the next steps are going to regenerate oxaloacetate, which then binds to the next acetyl-CoA. Remember, every glucose makes 2 pyruvates, and every pyruvate makes a acetyl-CoA. So when, for every glucose, the citric acid cycle is going to go around twice. We haven't really made much ATP, have we? We made the 2 during glycolysis and 1 here, and this goes around twice, so it goes 1, 2. But we haven't really made a whole lot of ATP, just 4. 4 isn't all that many. Now we're going to make that ATP. What we did make a lot of was NADH. So if you see here, what we're going to have is NADH come into the electron transport chain. The citric acid cycle takes place in the matrix of the mitochondria, so inside the middle bit of the mitochondria. The electron transport chain, or ETC, is going to happen on the membrane of the mitochondria, the inner membrane of the mitochondria, and the basics of what's going on here is we're going to use the electron energy of NADH to make a proton gradient. So let's start off, right? We have NADH come in. NADH is going to dump its electrons into a protein called complex 1. When it does so, that NADH goes back to being NAD and releases its H. The electrons end up on this coenzyme, which you've probably heard of. It's called CoQ. Some people take it as a nutritional supplement. Its formal name is ubiquinone. And ubiquinone grabs hold of those electrons, and it absorbs a hydrogen ion, and then it travels across the membrane to complex 2. In complex 2, we're going to dump off the electrons again and release the hydrogen. So here we are. All right. The electrons end up on this molecule up here called cytochrome C, and we release the hydrogen to this side. Now the electrons are going to travel through cytochrome C. Sorry, did I say that this is complex 2? This is complex 3. We'll get into what happens with complex 2 later on. There's no complex 2 in this. It's just 1, 3, 4. So now we have our electrons go to complex 4, and they're going to zap down here. You know what else we haven't talked about? You probably have heard that you need oxygen. That isn't going to surprise anyone that you need oxygen, and you know that you need oxygen to make energy. But here I am talking about all this making energy, and I haven't talked at all about oxygen. I talked about carbon dioxide. We know where that comes from. That gets released in the citric acid cycle from the carbons that you ate. Where does oxygen come in? Well, oxygen's about to come into play here. Oxygen is going to come in this way, and it's going to absorb these electrons, right? So the reason why we call breaking a bond oxidizing things is because those electrons have to end up somewhere, and oxygen is really, really good at absorbing electrons. So if you expose something to oxygen, oxygen will often just suck the electrons out of it, oxidizes it. What happens to oxygen when it becomes oxidized? Well, when it becomes reduced, because it's getting the electrons, when it does its oxidization thing, let's see. So the electrons go over here, they combine with oxygen, and then they grab 2 hydrogens from around here, and they become H2O. So the oxygen that you breathe actually becomes water in your body. What would happen if you didn't breathe oxygen? Well, think about it. If you didn't breathe any oxygen, where would the electrons go? They wouldn't go anywhere. They'd just sort of stall here. And then you'd have electrons stalled here. And you've had electrons stalled here, and you'd have electrons stalled here. And it'd be kind of like you've got like a highway with a car broken down on it. And when a big car breaks down on the highway and no one can get off the highway anymore, like the exits are blocked, what happens to traffic? Traffic backs up. If traffic backs up long enough, can anyone get where they're going? No. And if the traffic backs up in all of your mitochondria, you stop making energy. You stop making ATP. Because these hydrogens here, we've moved hydrogens up top, and we've taken hydrogens away from the bottom. Now, where do we have a higher concentration of hydrogens? Up top. Where do they want to diffuse to? Down below. We're going to use that energy like a water wheel uses water to drive a pump that will use that energy to make ATP. And that's this step here. This is the last step in the energy making process, and it's called oxidative phosphorylation. It's oxidative because the energy comes from that NADH, right? We used that NADH to move a bunch of hydrogens to the top of the membrane. These hydrogens now want to diffuse down below, but they can't because they can only move through a gate. Well, fortunately, we have a gate right here, but this is a very special gate. This gate is actually an enzyme called ATP synthase. As you might guess from the name, it makes ATP. As hydrogen moves through, just like when water moves down a water wheel, it causes the wheel to turn, and then you can use that turning wheel to do work, like drive a saw, run a mill, something like that. Here, what we're actually going to do is use the energy of hydrogens moving through to physically rotate the heads of this molecule. And it does. It actually spins in a circle. I've seen it happen. And as hydrogens move through, we're going to spin the head of this molecule in a circle. As this molecule spins in a circle, it's going to grab ADP, adenosine diphosphates, and a phosphate and slam them together. And we will turn ADP, which has 2 phosphates, to ATP, which has 3 phosphates. Let's see this work. Boom. See, we moved a hydrogen down, we turned our top, ATP left, we have an ADP in there. Let's do it again. The ADP is going to turn into an ATP. The head moves, another ADP comes in. That's how your body takes nutrients and catabolizes them to get energy out. Bullet point list for you here, big takeaway message. You need to know you need to know what metabolism is. You need to know the difference between catabolism and anabolism. You need to know what glycolysis is and what is produced from glycolysis. You need to know what the transition step is and what acetyl-CoA is. You need to know what oxidative deamination are and how the body deals with the ammonia that is produced in protein metabolism. And you need to know what beta oxidation is, how that beta oxidation plays a role in your body making use of energy in the form of lipids. You need to know what ketosis and ketogenesis are, how they allow your body to move energy that's stored in fat to other parts of your body. You need to know what the citric acid cycle is and what its inputs and what its outputs are. Remember, you're putting in acetyl-CoA. What are you getting out of it? Well, you make CO2, you make NADH, 2 of them, 1 ATP, and 1 FADH2. You need to know how NADH is used to generate a proton gradient, to move protons to one side of the membrane. You don't need to memorize all of the steps and exactly how the electrons go or anything like that, but what you need to know is that it is electrons moving back and forth across the membrane that generates this proton gradient, and you need to know where the electrons end up. The electrons end up combining with oxygen to make water. And you need to know that it is this proton gradient, the protons moving through ATP synthase to the other side, that drives ATP production. So for instance, what do you think would happen if I gave you a chemical that can bind a hydrogen ion and then move across the membrane and then release the hydrogen ion? There are actually several chemicals that can do this. What would happen? Well, now you've created an alternate pathway. Now hydrogen doesn't have to move through the ATP synthase to get across. That means that you've basically put a second spigot that on your water wheel that allows water to fall a different direction that doesn't turn the wheel. What happens to your energy levels? They plummet. There are metabolic poisons that work like this. Some of the most toxic substances on Earth actually work by short-circuiting this process. And they can be very dangerous. There are other metabolic poisons that will work by stopping oxygen from absorbing the electrons. Any of those things mean that basically your body can no longer make ATP. And while your body has a lot of ATP, it uses a lot of ATP. If you stop making new ATP, you've got like less than a minute worth of ATP. You will run out of energy and die in less than a minute if you stop making new ATP.